So for this learning module, we'll be looking at another example of how to compute the moment of a force about a particular point of interest using the vector formulation that was introduced in the prior learning module. So in this scenario, we have an individual trying to spin a merry-go-round. The geometry that's given to us shows the merry-go-round existing in the XY plane. So ideally, we would want to rotate it about the Z axis, but we'll see whether or not that is the case for the force that's applied. We kind of can know that this isn't going to work out, right? Ideally, in order to rotate about the Z-axis, you should be applying a force that's coplanar in the XY plane. If you just look at the geometry, the way that this individual is pulling it, it's going to tend to induce rotation about axes other than just the Z-axis. So let's kind of show that the calculations match our physical intuition. So I'm going to just make some notes here in terms of what we're given. We're given that the magnitude of the force for which we want to compute the moment is 56 pounds. We're given that it's applied at point A, which is located at coordinates 3, 4, 0, and those are measured in feet. And we're also given that the unit vector of the force has components minus 1/3, 2/3, and 2/3 respectively. And what we want to do is find the moment of F about the origin. So let's talk about how we would actually go about doing that. Key formula that we need is that the vector formulation for a moment says that we can compute it if we take the cross product of any position vector from the point of interest to the line of action of the force. Now, in this case, we know that we're computing the moment about the origin, and the only information that we're given, which would allow us to compute a point along the line of action of this force, is point A. And what I mean by that is just for the geometry that's shown, we have no way to write one of the infinite other number of position vectors because we're just not given the geometry of any point along the line of action other than A. So I can write an expression for the position vector from the origin to point A by simply taking for each coordinate of A, subtracting away the corresponding coordinate of the origin, and weighting that by the unit vector. However, remember that this process becomes very simple in the case where the tail of your position vector is at the origin, since all of those coordinates are 0. Basically, this position vector just becomes a vector whose components are the coordinates of A. So you can show that by just subtracting 0 away from each of these, but you'll get back to that original point. Now, in terms of determining what how you could express F in rectangular coordinates, remember that you can always take and write any vector in rectangular components by multiplying its magnitude times a unit vector along the intended direction. So all that I would have here is minus 56 divided by 3. I'm just going to scale this vector by 56. So multiply 56 on every component. That would be 112 divided by 3, and this would be 112 divided by 3. So hopefully that makes sense to everyone. All that I need to do now is compute my moment, which just boils down to computing a cross product, which we do by finding the determinant of a special matrix where the first row entries are the 3 unit vectors in the Cartesian coordinates. The second row entries are the components of our position vector, 3, 4, and 0. And the third row entries are the components of our force. Now, I'm going to show you how to actually compute this determinant one more time, but we won't actually make the calculations. I'll also show you a shortcut for doing it in Matlab. You would have access to similar functionality in whatever calculator you're using as well. But remember, the way that you determine the determinant of this matrix is to walk along the top row at each position, cover the column, and cover the row, which will create a 2x2 matrix, and determine the determinant of that 2x2 matrix. That will be the component of the unit vector that you're covering. The key point is, as you walk along, you alternate signs. So start with positive for I hat, go with negative for j hat, go with positive for k hat. So how would we write that? We would say that the moment has an I hat component, which is given as the determinant of that 2x2 matrix. So 4, 0, 112 over 3, 112 over 3, minus j hat times the determinant of that 2x2 matrix, 3, 0, minus 56 divided by 3, 112 over 3 plus k hat times the determinant of this 2 by 2 matrix. 3, 4 minus 56 divided by 3 and 112 divided by 3. So when we have 2 by 2 matrices, we determine their determinants by taking the difference of the downward diagonal product and the upward diagonal product. So this will just be I hat times 4 times 112 over 3 minus 0 times 112 over 3. So that 0 term will just go away, and we have our coefficient of I hat there. In a similar fashion, for the j hat direction, it will be 3 times 112 over 3 minus 0 times minus 56 over 3. So again, we get a cancellation. We get some easy math there. These will cancel and give us 1. So we know that j component should be 112. Again, we're not actually going to compute this. I want to show you how to do it in Matlab. Those should be parentheses, sorry. Product along this diagonal, 3 times 112 over 3 is just going to be 112 minus 4 times negative 56 over 3, which will just be plus 4 times 56 over 3. So that's going to be a little more complicated of a calculation. But let's see what way that we could do this in Matlab if we wanted to. So I would begin by defining my position vector. Now I define position vectors in Matlab by using square brackets to tell it it's going to be a vector. If I want to create row vectors, I separate each entry by a comma. And I'll use a semicolon to suppress my output. But if you notice, that variable is stored in the workspace. For the first vector, I will take, and just to make sure my math was right, I will scale the unit vector by 56. And the unit vector that I was given is minus 1/3, 2/3, and 2/3. And then what I want to do is take the cross product of R and F. And I do that in MATLAB through the cross function. And if you notice there, we get the X, Y, and Z components of that moment. And the X component rounded to 3 sig figs is 149. The Y component is minus 112. And the Z component is 187. And that will take on the units of the product of whatever units our position vector was in times our force vector. And since we're in the empirical units, that will be in foot-pounds. And you can kind of check, like we knew what the one answer should be. We knew that the j hat component would be minus 112. If you wanted to check that I hat component, you could look at our by hand work. So it's 4 times 112 over 3, which is the 149.3, same answer we got. You could do the same thing for the z component, or you could just trust that whoever wrote the cross function in MATLAB didn't make an error. So hopefully that makes sense. And there's another review of how to compute moments using the vector formulation. Again, we said that ideally, if you want the merry-go-round to operate as intended without putting undue stress on the underlying ball bearings and whatever hardware is actually allowing it to rotate and maintain its longevity, you would only want a component of your moment in the z-hat direction. However, what's happening is rather than this person spinning it purely by applying a force in the xy plane, they're kind of jerking it upwards, which is causing it to rotate in a way that's not intended. So the math did work out to kind of follow up on what we assumed.